At the final battle in a war game, it's recording, I did it. Two opposing armies led by General Rose and Colonel Cole. I love the way, I can't remember who it was, but one person consistently referred to Rose as she. Just, I don't know, we don't know based on this, but I quite like that. Are facing each other across a wide river. Scorby Beck. Each army consists of 4 divisions. The commander of each army needs to send some of his troops north and the rest south. Each commander has to decide how many divisions, 1, 2 or 3, to send north. It's so dramatic. Intelligence information is available on the number of thousands of soldiers that each army can expect to have remaining with each combination of strategies. Thousands of soldiers remaining in R's army and thousands of soldiers remaining in C's army are given in the tables there, depending on each of the choices. I am voting in favour of both of them, doing option 2, because that way the most people survive, and we'll just all go home, and or maybe have a picnic by the banks of the river instead of all this fighting. Construct a table to show the number of thousands of soldiers remaining in R's army minus the number in C's army, so that would be the excess for R's army, as in how many more soldiers than C R has at the end of it for each combination of strategies. So, well, that was, we all got these 2 marks really. I think that is just about doing a little subtraction. Sum, it's the number remaining in R, so our table, nice, is going to be 1, 2, 3 there, 1, 2 and 3. This table is much too small, but I just want to be able to see all of it at once. So we've got, what have we got, 15 take away 20, is that right? 20 take away 15, 30 take away 10, 25 take away 35, 50 take away 50, 35 take away 25, 30 take away 10, 15 take away 20, and 15 take away 40. So that's what our new table looks like at the end of the first round of doing that. Okay, then it says, that was 2 marks for that. Then it says, the commander whose army has the greatest positive excess of soldiers remaining at the end of the game will be declared the winner. Explain the meaning of the value of the top left cell in your table. And hence explain why this table may be regarded as representing a zero-sum game. So that minus 5 as the top figure, what does that mean? Well, that means that this is the excess number of soldiers that R has, isn't it? That General Rose has. So this is, his excess is minus 5, so it means he has 5,000 fewer soldiers than the other person. So that's the first bit. That's when we say explain the meaning of the value. That's what we have. Or you could say C has an excess of 5,000, whichever way you want to call that. Hence explain why this table may be regarded as representing a zero-sum game. We didn't do this terribly well because we tended to be a bit kind of unclear about our reasoning for this. This is one of those things, if you're asked to explain why something is a zero-sum game, then they're looking for just a straightforward calculation. Okay, so what we're saying is that this tells us it's a zero-sum game because R would have 5 fewer than C. We could say minus the minus 5 for R plus the 5,000 that would be the excess that C has equals 0. And that's our zero-sum game. Minus 5 for R, and the 5,000, the plus 5 for C, adds up to give us 0. Therefore, we have a zero-sum game. Okay, that kind of question is simply looking for that. They're not looking for an explanation that goes into detail about one person's gain is covered by another person's loss. They're not looking for a more general thing. It was a hence. So it was a specific, referring to that example, state y it's a zero-sum game. And you could generalise that as well to say it applies to the whole table. Part 3 said, find the play-safe strategy for R and the play-safe strategy for C, and then if C knows that R will choose its play-safe strategy, which strategy would C choose? So most of you did this little bit on the table that you've got in the other box, and that was absolutely fine. The mark scheme said expect to see this in the box at the top. Remember the thing that we talk about here, we're looking for the row the row minimums as being minus 5, minus 5, minus 25, and we're choosing, no, it's minus 10, sorry. I didn't read the table there. Minus 10, minus 5. And we're choosing the biggest of the row minimums. So it'll indicate that you've made a choice of that one. Here we're looking for the column maximums, which would be 20, 10 and 20, because that's the worst possible outcome for C. And we're looking to minimise the worst thing that could happen to C. So that would be the 10 there that we would have. And the question said, identify the play-safe strategy. So for R, it's strategy 2. And for C it's also strategy 2, and then you had a little box at the bottom to say if C knows R will play safe, which strategy should C choose? So C knows that R is always going to do that middle row. If that's the case, the best possible outcome for C is the option 3, isn't it? Because minus 5 means that C ends up with an excess of 5. So C should choose 3 in order to make sure if C knows that R will always play safe. There you go. They gave 5 marks for that. So there was a mark each for the column maximum and row minimums, another mark for identifying the play safe strategies, each of them, and a mark for this bit at the end. Right. Now we go on to the next bit of the game. I'm on a new page for this. One of the strategies is redundant for one of the commanders because of dominance. Draw a table for the reduced game once the redundant strategy has been removed. Label the rows and columns to show how many divisions have been sent north. Okay, so the first thing we need to consider, we're going back to this now, which is the redundant strategy. So we're looking for either row or column dominance. It hasn't suggested which we're looking for. Row 1 isn't better than row 2, is it? Because it loses out. Those two are both worse. Row 1 and row 3, if we compare those, no, because although row 3 is better than row 1 for the first 2 options, it's worse for the third one. Row 2 and row 3, no, we've not got dominance there. 20 is more than 5, but minus 5 is more than minus 25. So we don't have any row dominance at all. What about column dominance? Now remember, with columns we're looking for the most negative thing. That's better. The more negative is better. So minus 10 is better than 20. 0 is worse than minus 5. So we don't have a dominance between those two. Minus 5 is better than 20, but 5 is worse than minus 5. So there's no dominance relationship between 1 and 3. 1 and 2 then. Minus 5 would be worse than minus 10. 5 would be worse than 0. 20 would be worse than 10. So that's where our dominance lies. But what a few of us did is we picked the wrong thing to remove from the table. So we've got to think which of these two options is better for player C. For player C, the more negative it is, the better. So can you see that the best option for C is option 2? Option 2 is always better than option 1 for player C. Does that make sense? So our new table is going to include columns 2 and 3 and rows 1, 2 and 3. And we need to recreate our table, so we've got minus 10, plus 20, 0, minus 5, 10, minus 25. So that was the answer to part 4. 2 marks. There was a method mark for doing a table with 2 columns and having the wrong one in there, so a few of you had 1 and 3. Fortunately, it didn't affect anything later on in the question if you'd made that mistake. So we're on to part 5. Part 5, now here we go. We're now into linear programming problem based on this. So, a mixed strategy is to be employed on the resulting reduced gain. This leads to the following linear programming problem. Maximise m, which is n minus 25. I've just realised something that I hadn't completely twigged as I was marking it, but that was a bit daft of me. That actually, if you'd got that bit, if you'd got the wrong 2 columns, does that make the next part of this more difficult? It quite possibly does, doesn't it? If not impossible, yeah. Anyway, right. So it leads to this problem, which it has a very familiar feel to us, doesn't it? This is what you get when you do these kind of linear programming problems from game theory. Interpret what x, y and z represent and show how this expression was formed. Right, so, well, the first bit, what do x, y and z represent? X, y and z add up to 1, don't they? And what things is it that add up to 1 when we're dealing with this stuff? It's got to be probabilities. That's the clue that we're dealing with probabilities here. So the first thing to remember is x, y and z are definitely not the numbers of divisions that they're sending or anything like that. They are the probabilities with which each of the options are employed. So that's the first thing to say, that you're going to write x. I actually wrote this in full detail here, so I wrote x is the probability of R sending 1 division north. Of course, that means also sending 2 divisions south, because we're talking about north, aren't we? But that's enough just to say that. Y is the probability of sending 2, and Z probability of sending 3. So that's the first bit for our, I think, first mark after that. Now, explain how the table, how the equation came up. Well, look, we've got n minus 25 in here. So there's a 25 thing going on. We know that to turn one of these tables into a linear programming simplex problem, you need all of the values to be positive. So what we're clearly going to do is we're going to add 25 to each value. That's why we're taking away 25 again at the end to undo the effect of adding 25. So that gives us our matrix that looks like, and hopefully nice things will drop out of this now, 15, 25, 35, 45, 20, 0. That's our new matrix. And it was, wasn't it? These numbers just didn't appear, did they? I hadn't quite twigged that. If you got the wrong 2 columns from the previous bit, you never got to see 15, 25 and 35, but there they are, magically appearing in that first column. And so, we've got to think, what does that first column mean? That is, if C chooses 2, then R's expected winnings are 15x plus 25y plus 35z. And we're trying to minimise, we're trying to play safe. So we're looking to maximise the minimum that this could be. therefore we want 15x plus 25y plus 35z to be greater than or equal to n. They didn't care too much about the details of how you explain that last bit. And it was, after all, only 2 marks, all of this. So that's... I felt there was quite a lot for 2 marks there if you're going to do that thoroughly. Right, so now we're on to part 6, is that right? Part 6 says, a computer runs the simplex algorithm to solve this problem, and it gives those values. Describe how this solution should be interpreted in terms of how General Rose chooses where to send his troops. Calculate the optimal value for m and explain its meaning. Right, so based on this, we've got x as being 0.5385, is that correct? Yep. Y is 0, Z is 0.4615. So what does this mean? This means R should send one division north with probability 0.5385. Never send 2 divisions north, and send 3 divisions north with probability 0.4615. We should be playing randomly, of course. That's always part of this, isn't it? That you should apply the strategy randomly. Right, that's the first bit done, and that gets us 2 marks for explaining that. We're looking also for the optimal value of m. So if you sub that into your equation, then it comes up with m as being, little m, as being 24.2325. So big M, which is m minus 25, is minus 0.7675. There we go. I know you added it for no apparent reason. Then the question finally said, interpret this, calculate the optimal value for m and explain its meaning. So the 2 marks here are for explaining that meaning. Now, this is the bit where I disagree a little bit with the wording of the mark scheme for this. So I'm going to say what I think it is, and then I'll tell you what it says on the mark scheme. I think that this should be R. How do you spell loses? Is it double O? Right, don't read my answers here because I wrote double O there. That's right. That looks right. That feels good. Right. I wrote R loses on average 768 men compared to C. So C expects to have 768 men more than R. That's what it means if we play this game lots of times. On each game that it's played, the expected outcome is for R to be down 768 compared to C, and C to be 768 up compared to R. Because remember, that's how we set it up, isn't it? We set it up so that the values in the table were expressing the excess amounts. How many more men are had than C at the end of it. Okay? So that's how I would have ended that bit. That was for 1 mark. The mark scheme says R can expect to lose sorry. That was great. R can expect to lose 770 soldiers. C can expect to win the same number per game. You had to have a comment that interpreted it in terms of both R and C. Can you get why I disagree with that? And especially the C can expect to win the same number.
C doesn't win, just doesn't lose though.
Exactly. There's no winning of soldiers going on here. There's no armies increasing in size. That's not what the game is all about.
Really
the game is
either.
trying to not lose soldiers. So I disagree when it says C can expect to win the same number. I might be wrong. There may be something that I'm not interpreting right about that. So, you know, internet world, if you want to comment on this video and tell me that that's the wrong interpretation of it, then I can delete the comments quite easily. Right. Elizabeth does not have access to a computer. It's a tragic story. She maybe had a computer, she maybe dropped it in the wide river that the two armies were assembled either side of. She says that at the solution to the LP problem, 15x plus 25y plus 35z must equal 45x plus 20y, and x plus y plus z must equal 1. This simplifies to give y plus 7z is 6x and x plus y plus z equals 1. Fine. Explain why there can be no valid solution of these simultaneous equations with x equals 0. Right? Well, let's see what happens if x equals 0 in this final little bit of the question. I'm on the very back page of the book now. If x equals 0, then y plus z would be 1. I've just written z plus z. Y plus z would be 1, and y plus 7z would be equal to 0. Okay, well, fair enough. They are simultaneous equations. There's no reason why we shouldn't solve those. This one implies that y equals minus 7z. If I sub that into the first equation, minus 7z plus z equals 1, giving me minus 6z equals 1, and z equals minus a sixth, at which point we're supposed to go, aha, because x, y and z, as we've already stated, are the probabilities of playing each strategy. So z cannot possibly be equal to minus a sixth, because it's a probability, and probabilities must be between 0 and 1. So at that point, but z must be between 0 and 1, therefore not a solution. There we go. So showing that you've got this basic inconsistency. That was only 1 mark, wasn't it? 6 part 7. And finally, 6 part 8. This is the bit of this paper that on results day, or not on results day, on the exam day last year when I did this, this is the bit that left me scratching my head about this for some time afterwards. And we've talked about this a lot in our maths office, and I'm still not entirely happy about it, but I'm prepared, well, I don't know, I'm not prepared to concede it. The bit now, Elizabeth tries z equals 0 and gets the solution, x equals a seventh and y is 6/7. Explain why this is not a solution to the LP problem. Now I think I'm being, I don't know, maybe I am being pedantic. But I'll explain what happens with this. What you do at this point is you take these values and you sub them back into the original equation and see the value of m that you get. So if we have z is 0, x is a seventh, y is 6/7, the value of m that we get, it fits them, the equations are satisfied, everything works, and we get m is minus 1.43. Meaning that R would expect on average to lose 1,430-ish soldiers compared to C each time the game is played, which is worse than part 4. And that's it. That is the end of this question, because they wanted you to work out that that gave a value of m of minus 1.43 and to state that that was worse than the answer found in part 4. Therefore, it's not a solution of the LP problem. Now, the slight problem that I have with this, and maybe it's a bit fussy, is that it is a solution of the linear programming problem. It's not the solution of the linear programming problem. Do you see where I'm going with that? It is a solution. It fits the linear programming problem. It's not the solution because it's not the best, it's not the optimal solution, it's not the one that maximises it. It's still a solution of it. That's my problem with this last bit. Now, when we talk about this in the office, it comes back to the fact that the LP problem is to maximise m. And so a solution to the problem that maximises m, well, it's not a solution to the problem to maximise m because it doesn't maximise m, because there are bigger values of n. But I still feel uncomfortable with this as a thing. Does that make sense?
No, I disagree with you.
I know you disagree with me, but you're just doing that to be smug.
No, I just disagree with
I still think it is a solution, but not the solution. But anyway, that's what they wanted, and that would have been 1 mark, because I think, you know, you would have found m equals minus 1.43 anyway, regardless of how you feel about the wording of the question. 20 marks out of 72 on that one question. 20 marks, well that's more than the gap between D and A star of the grade boundaries of that paper. It's more than the gap between, comfortably more than the gap between E and A in this paper. Wow. Right, is that clear? Do you never want to see that again? And that's game theory maths.